using rough set theory. That means I use those domain knowledge, I encode into neural network parameters so that my network starts from the very beginning with a good initial input rather than starting from raw parameters. And therefore, I'm expecting that its learning time will be much more faster as compared to if I would not have used those domain knowledge encoded in the neural network parameter. Now, since we have seen this multilayer perceptron may get stuck to local minima because its parameters are being corrected using gradient descent search, which may have a chance to get stuck to local minima problem. Therefore, and also this is gradient descent search is very slow when the number of nodes and layers increases. Therefore, in order to circumvent this, we can use genetic algorithm-based learning. That means I forget gradient descent search. I use genetic algorithm-based learning. That means I consider there are as a solution different neural networks with different sets of parameters. And then I use from this update, I use the same parameter one. Then I again also use genetic parameter tuning for this low, medium, high. I use genetic algorithmic parameter tuning for this boundary selection also. And as well as I use genetic tuning for this learning of this neural network parameters also. So see, this will be very synergistic integration between these four rules as I explained to you. Now let's see its result. Synergistic integration. Now let's see its result. What will be its merit? Merit is that it enhances the classification performance. Number one. Number two, training time improves. Number three, network compactness. What is network compactness? That means you have least number of only relevant network parameters. That means you do not have redundant nodes and links. And if you have compact network means the rule that would you generate from using neural networks based on output to input, it will have less ambiguity. So therefore, if you have more number of nodes and links, some of them are not equally important or some of the redundant, so they create problem and they create ambiguity. So it enhances the classification performance, it enhances the training time, and it improves the network compactness. Now let's see one. So it generates rules of higher accuracy, rules in linguistic term, generates smaller size rules. Rules will be of number of rules will be small and less confusion. So these are the merits because unless you have application specific merits, there is no question of making synergistic integration. So for example, we use modular rough fuzzy evolutionary MLP. What is MLP? So that is what is the principle of modularity? What is the principle? That you split a learning task into several subtasks. Train a subnetwork for each subtask. They integrate the subnetworks to generate the final solution. Very carefully you notice. That means if you have a one network of say a large number of input, a large number of output, then it is very difficult to manage, to train itself. And it can get to local minima and so on. So instead of that, I can split a learning task into simple subtasks, several. And for just several and for simple subtasks, I can train a simple network. And if the network is small network, then it is learning time is very fast. I can handle it nicely. Then I train this network and integrate these small networks corresponding to each subtask, and they generate the final solution which will handle the final task. So basically it's called divide and conquer strategy. That means if you cannot conquer the whole problem, then you conquer it by splitting into small sub-problem and then integrate it. So here the challenging issues comes how to split it and then how to integrate it. So you want to get rid of one problem, but at the same time you are introducing some other problems which are expected to have less cumbersome. So approach involves effective decomposition of the problem such that sub-problems would be solved with compact networks. Compact networks means small network, that means number of nodes and links very minimum, so that you can handle it. It's fast. The effective combination and training of the sub-network such that there is a gain in terms of both training time, network size, and accuracy of solution. So there are three gains we are expecting. That's why we are taking this trouble. So what are the advantages in machine learning point of view? It's accelerated training. Final solution network has more structured components. That means ambiguous, redundant nodes and links are absent. So more structured. The representation of individual clusters, irrespective of size, importance, is better preserved in the final. This is most important. In machine learning problem, that is a very common problem that if you have two clusters, one is bigger and one is much smaller, then always you will get bigger, good recognition score, but individual score may not be good. That is, the bigger cluster swallow this smaller cluster. That means its identity doesn't get reflected. You get overall recognition score very high, but at the cost of this smaller cluster recognition. So individual recognition score will be very poor, but overall will work. This is a very common problem in machine learning when you have got two different sizes of clusters. Imbalance, sometimes it's called imbalance clustering. So here what we do, since your total learning task has been split into two subtasks, so each subtask takes care of these individual classes. That means the identity is better preserved. Identity is better preserved because within individual subtask you are just taking care of their requirement nicely, instead of considering the whole process as one learning task and then forming a one network. So representation of individual clusters, irrespective of size and importance, is better preserved in the final solution network. And the catastrophic interference problems of neural network learning in case of overlapping patterns, that is, you are switching from here to the catastrophic interference is reduced. It's not removed, but it is reduced because you have now separate networks for separate clusters, for example. So how do you do the strategy is divide and conquer. You split M class problem into M2 class problem. So if you have got 3 class problem, you have 3 2 class problem. That's why instead of deriving one network from 3 class output, you need one 3 2 class problem. That means whether this class belongs or not. 3 such. So that is M simpler subtasks. Then granules generated from the data using rough set theoretic rules are encoded to form the subnetworks to solve each subtask. Then the subtasks are trained and integrated using genetic algorithms with variable mutation. I will explain why variable mutation to form the solution network for M class problem. So I take M2 class problem, then for every class I have a smaller network derived based on the rough set theoretic information extracted from the data. Then subtasks are trained individually and integrated using genetic algorithms to form the one. And while we make the genetic integration, we use variable mutation. What is variable mutation operator? That means while I train the individual network for individual classes, I have already paid for every network, every link one. So when I am integrating them, I want to make sure that the link that we already paid for much to generate do not get much change. Whereas the link that I want was not present that time, but because of the integration, those networks links are coming up. So those for them, I want to them get changed frequently. That means mutation for the already trained one will be less probability. And mutation of those which I like to change will have high mutation probability. That's why I'm calling it variable mutation operator. So as an example, it's a 3-class problem. I split it into 3 2-class problem, class 1 subnetwork, class 2 subnetwork, class 3 subnetwork. Then we integrate them in the same input. Now 6 hidden nodes, 3 output, links to be grown, dot, 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 links of value already preserved. So I get for them low mutation probability, for those high mutation probability. And therefore I get a final 10 network, for example, here. So I have grown this intermodule link. So all those dotted were not there. Only few of them have grown up. So that's how I get the number of links. If I would have generated one network of just 3-class problem, then I would have all those links possibilities, all those links. So here now you see that links are sparse. That is, network is compact. So how do we? Let us buy from the market fuzzy MLP. So modular rough fuzzy evolutionary one. I have fuzzy MLP, I use rough set theoretic, I use modularity concept, and I use genetic algorithm for variable mutation. So many things are integrated. So modular network design using 41, basic network is fuzzy MLP. That means multilayer perceptron with linguistic input and linguistic and your overlapping output. Rough set theory used to generate crude decision rules in the form of rough granules representing each of the classes. And as I mentioned before, a class may have more than one number of conjunction. That is, a class may be characterized by more than one such granule. That means if the classes are elongated, it will have more than one such granules. For example, the knowledge-based subnetworks are concatenated to form a population of individual subnetworks. So this population is a solution space of genetic algorithm. Final solution network is evolved using genetic algorithm with variable mutation. As I mentioned to you, the bits corresponding to intermodule links already evolved have low mutation probability, and the bits corresponding to intermodule links have high mutation probability. So let's see how knowledge flow in modular come. Suppose this is a toy example. This class is represented by this conjunction. So this is the network. First feature is low and second feature is medium. First feature is low, the second feature is medium, or first feature is medium, second feature is high. So this or this. So this two makes this one this network, and these two are corresponding to region R1. Region R1. These two conditions means these two regions. Similarly, for class 2 C2, second feature is medium. Second feature is medium and first feature is high, or this. Similarly, second feature is low and first feature is also low, high. So these two constitute these two regions. So after partial training with genetic algorithm, these shapes get changed. And then after final training of the concatenation network with high mutation probability, dot, 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 low mutation probability, then we get a variable mutation evolution of the ultimate network, final solution network. We get this feature space. So we started from crude description of these two classes, C2, C2, C1. Then through genetic tuning, I get this feedback out of those network. Then I concatenate these two one, then I get solution network of the one of this. So this is a toy example of showing how knowledge is flowing with iteration and with all this here. So this is a nice example of the modularity concept based on rough set theory, granule or neural network. And then same speech data when you use for one, and I'll be using this data for many pattern problems because this is a very benchmark data showing so much of overlapping. One, you see that 3-feature 6-class problem. We have multi-layer classification training, testing, multi-layer perceptron, fuzzy multi-layer perceptron, rough fuzzy multi-layer perceptron, and modularity. And if you see, look at this one with training set, as you grow from one, training accuracy is increasing. Similarly, testing accuracy is also increasing. Similarly, if you go by the training time, multi-layer perceptron, fuzzy multi-layer perceptron training time because of the membership concept, all you have to store, so the computation time increases. But fuzzy MLP, the rough fuzzy MLP, it reduces. Modularity is further reduces. So nicely you see the training time reduces from here to here, here to here, the modularity. So multi-layer perceptron, rough fuzzy multi-layer perceptron, that is you are using rough encoding in the neural network parameters. You are reducing the training time. Similarly, for the modularity, it is reduced for that time. Similarly, network size, here network size is increased because you are using fuzzy, then rough fuzzy, then this is modularity. So network size has increased, is reducing one number of links. Now look at the number of links is an increase. If you draw the graph of number of iteration, correct classification, MLP, fuzzy MLP, modular. So you see the improvement of 3/2, improvement over 5/4 using modular concept for speech data. Similarly, if you compute the histogram of the links, here's the links, you see that in case of modular concept, most of the links are 0. That means a very sparse network. So it's called structured. Number of links is very small. But whereas other fuzzy MLP, it's a distribution link. That means all links are grown there or are there. So it's called unstructured. Number of links more. So it's a more compact network. So if you have a more compact network, means your number of ambiguous rules will be less. This is a typical example of the compact network. If you look at this, you have so many input, 9, output 6 classes, but you see all links have not been grown. Even if you have some links here also, you see that thing very interesting. It's called compact network. So that means all links which you would have required if you would have developed one simple network for 6-class problem. So connectivity of the network obtained for 6-class problem using modular rough fuzzy network. Look at this one. This link is grown because after that there was no grown up. So it is of useless basically. This is a nice example. So this was our rough neural computing book from the same our publisher from our group from Poland we worked on. That was in 2003. That means we call it Computing with Words. How to ISO. This is a highly cited book. It is one. Then let's consider generalized rough set. If you have remembered yesterday, before generalization, I get the introduction in my last session on the previous lecture. So, and then I said that before I go for generalized rough set, I will explain the individual granular concept and their representation. Now, generalized rough set. What is rough set? In real life problem, as you mentioned, the set and granules could be either or both fuzzy. Because Professor Pavlov's definition of rough set was that granule is crisp, set is crisp. But in real life problem, we have seen the both set or granules or one of them could be fuzzy. If one of them is fuzzy, then the lower and upper approximation would be fuzzy. That is, they will be fuzzy set. And if they are fuzzy set means they can be represented by membership function. So in real life problems, the set and granules could be either both or fuzzy. That is, you incorporate fuzziness in set or granules of it. For example, in an image, I give you the same example again. Since it is a gray tone image, we cannot define the boundary between two regions because the region boundary is sinusoidal variation. So here comes the significance of fuzzy set. Similarly, if you work with a 3x3 window in an image, you can put 3x3 windows distinctly or by putting overlapping. So if I consider 3x3 window is a granule, so granules could be discrete, granule could be overlapping. So here is my rough set theoretic concept that I explained last time. So it's a granulated domain, x-axis, y-axis. They constitute the beta feature space. If I would have added one more axis, then the size of the granules would have been changed. This is my lower approximation. That means granules definitely belonging to this set as marked by the orange line, the green line, and granules as marked by the orange line. They indicate the granules definitely belonging as well as possibly belonging. That means these upper granules minus lower granules I call boundary granules. So they create problem in making a decision or in defining the set. So now I'll show that how fuzzy set can be incorporated in the set theory, that instead of crisp set, I call it a fuzzy set. Similarly, in the granule is crisp granule, I can call it a fuzzy granule. So I will see that if both of them are fuzzy or one of them fuzzy, how do they behave? This is very important. Please carefully. Now it is a crisp set, crisp granule. Therefore, my lower approximation is a crisp. There is no idea, there is no fuzziness. And upper approximation is also a crisp, which is a superset of this lower approximation. Lower approximation is a subset of upper approximation, but both are crisp. Now I will show one by one. So set is crisp, granules are crisp. I call it rough set. That is the definition of Pollock's rough set. Now I call it, let's set be fuzzy and granules have crisp. Then I call it rough fuzzy set of X. Then if set is crisp but granules are fuzzy, I call it fuzzy rough set of X. Now granules is fuzzy and set is fuzzy, that is both are fuzzy. We call it a fuzzy rough fuzzy set of X. Fuzzy rough fuzzy set of X. So it's called generalized rough sets. Obviously, if you see that this is the simple case, there is uncertainty is less. Uncertainty comes only from the granularity. There is no fuzziness. Now fuzziness introduced here, fuzziness is introduced in the granule, then fuzziness is introduced in both set and granule. So as we go from here, it is becoming expensive, but it handles uncertainty much better. So depending on your problem, how much money you will spend, how much uncertainty you need to handle, you go by this accordingly. If you do not need any kind of, simply go by this. If you need a boundary of fuzziness, etc., go by this, etc. Now let me explain the characteristic of this set in terms of lower and upper approximation. Note it very carefully. Let's consider origin equivalence relation. So set is X crisp, granules have crisp boundary. So this is a simple example in one-dimensional representation. 0 to n, that means 0 to 1, this is one granule, here to one granule, here to, so all crisp granules. There is no overlapping, crisp granule. Set are crisp, and set is also crisp, the black line. So set is crisp. This is a granulated domain, crisp granules, and over this crisp granulated domain, I define a set 1, 0. That means this set belongs to granule. This set, this granule belongs to this set. This granule belongs to the set. This granules, this belongs to this set. But this granule, there is a doubt because it doesn't completely belong to this set. Similarly, this granule does not, this. So granules from here to there, they do not belong to this set. Granules from here to here, they belong to this set. But this granule is a boundary granule. So I can put a green line here. So the black and green, it constitutes my lower approximation of this granule. Because these are the granules, they definitely belong to this set. Similarly, I can put this lower approximation plus this boundary granule together is called red. So black, red is called upper approximation of this set. So this set black is characterized by lower approximation green, black and green, upper approximation black and red. So this pair lower and upper, it is referred to as rough set of X. So my X is a crisp set, but it has rough description in terms of lower and upper because the set is defined over a crisp granulated. This is Paulak rough set. That's what I wrote it. Lower approximation equal to set of all U universe belongs to the universe where granules around U all belongs to X. So any U, you take a U belonging to a granule, so the entire granule belongs to it. So all U belongs to it. All U belongs to it. But here, not doesn't work. Similarly, upper approximation, rough, is a lower upper approximation on granules U such that the granules containing this and this intersection of this set X is a non-empty set. So this is my, so if you take this as per the definition of, that means you take all those granules where these granules have a, with X intersection of any granule intersection is a non-empty, whether you take these granules or you take these granules. If you take the intersection, it is a non-empty set. Now your next level you come. Set is fuzzy. This is characterized by membership function. And granules are crisp. Now you see that up to 1, 2, 3, these 3 granules, they definitely belong to the set 1. But now let's consider this granule. Here, all these membership values, if you look at this, there are membership values. You take from these membership values and take the minimum, inferior, and take the supremum. So if you take the minimum or maximum, inferior, supremum, you get the lower approximation. That means any granule belonging to one has a membership value definitely belonging will be indicated by the green line. That means it cannot be less than this. Similarly, granules belonging to the red one, they will indicate the upper approximation. That means it cannot be more than that one. Similarly, for here, it comes to, you take all the membership values, take the minimum, you take all the maximum values, that is the maximum. So it is a staircase green line. It gives the lower approximation, staircase black and the red. It called is upper approximation. So this lower and upper, they constitute what is called rough fuzzy set of X. So here set is fuzzy. So similarly, what we define here, lower approximation equal to inferior over all those granules you take. So of any element U, what will be the lower approximation? You take the granule with which it belongs and you take its inferior over all these elements belonging to this. So this is the inferior value, this is superior value. Now come to The granules are overlapping, but set is crisp. Very interesting. Now you see that here this red and green, they are parallel to each other, but they are not parallel to the black line because their tilt is determined by the degree of overlapping. If you have just larger amount of overlapping between the granules, then their tilt will be more. So this pair is referred to as fuzzy rough set of X. So here, what are the characteristics? You take the lower approximation, upper approximation as follows. So here, this is the membership value of an element U belonging to the granule Y, such that all over granule it wants. And this inferium, this is the membership value of a granule Y belonging to the lower approximation. So if you take the product, that gives the membership, gives the membership value of a granule, membership value of a point U belonging to the granule Y, that is belonging to lower approximation. And if you take the summation over all granules, such one, it gives the membership value of this point Y for belonging to the lower approximation of the set. Similarly, for upper approximation, you take this value instead of inferior, so P1. And it is C when it belongs 1, otherwise 0. Very interesting. Now, so the first term, as I mentioned, membership value of an element U for belonging to a fuzzy granule Y. Second term, membership value of a fuzzy granule for belonging to the lower approximation. And if you take the product, membership value of an element U for belonging to fuzzy granule Y, which is contained in lower approximation. And your summation over all Y, all granules, the membership value of an element belong to lower approximation. Similarly, if you take the both are fuzzy, then it becomes overlap, oblique. If you look at this, this was staircase, oblique, vertical, staircase, horizontal, vertical, horizontal, vertical. But here, because of the overlapping of the granularity, is it oblique. Maximum level of uncertainty. So this is referred to as fuzzy rough set X. So depending on your uncertainty, depending on your fuzziness, depending on your granularity, you get one. So similarly, so again, let me remind you, if there is no granularity, there will be no roughness. Granularity is coming because of the granularity, only is roughness is coming. Similarly, if there is no fuzziness in the set or granules, then I do not need to go by all those things. If only fuzziness comes in one of the set or one, then accordingly I get one. And as you can see that if one of them is fuzzy, the lower and upper becomes fuzzy. If that is in earlier case, that is crisp, lower upper. Here it is fuzzy, here it is fuzzy, here it is. So I have this, now I can define the roughness estimation, 1 minus cardinality of lower divided by cardinality of upper. As you can see, when it is a crisp set, then you can count number of granules belonging to lower, number of granules. But when it's a fuzzy set, I get one fuzzy addition. That is, I take the membership value of all elements and then I add them. So it's called fuzzy cardinality. That is, instead of number of counts, you get the number of membership value. So the summation of the membership values of individual granules, depending on the degree of belonging, you get this value. So the lower upper approximation, lower. And this vague definition of X, as I mentioned before also, I'm again repeating, the vague definition of X in the universe U in terms of lower and upper approximation signifies the incompleteness of knowledge about U. Why incompleteness? Because you have made it granulated. So you have approximated the one, and you have made it granulated with respect to some relation, and you have used a subset of feature set. You do not know the entire all feature. If you would have known all features, then this approximation would not have been there. So having this approximation, you have a vague definition of any set defined over this universe, and it signifies the incompleteness of knowledge about the universe. And therefore, to make a decision, you like to minimize this incompleteness. If we minimize this incompleteness, you make a decision. Therefore, you will see that whenever we are using this rough fuzzy entropy, then we always try to minimize this entropy value in order to make a decision. Again, let me reiterate, we are not considering probabilistic uncertainty here. We are not considering probabilistic uncertainty. That means uncertainty arising from randomness of occurrence of an event. We are only considering uncertainty arising from granularity, uncertainty arising from overlapping concept. Keep it in mind. So based on that, we can define entropy. We can use two types of gain function. One is logarithmic gain function, one is exponential. What is logarithmic gain function? Suppose a probability of occurrence of an element is pi, then the amount of ignorance is 1 divided by pi, and it could be arguably 1 minus pi also. That means larger the number, larger the value of probability, amount of ignorance will be less. So if I use 1 divided by pi, then we go by logarithmic gain function. If I use 1 minus pi, then we call by exponential gain function. So if we plot this, I will show the plot one. So if you go by this, the properties will be given a non-zero value. If one of them is non-zero, then the other value will be just also non-zero, but I cannot define. It can take any non-zero values. If one of the values is 0, then the other values is also 0. They are positively correlated. Non-negativity. See, logarithmic entropy, exponential entropy less than or equal to 0, and 0 comes only when both the roughness values are 0. Continuity. They are continuous function of the roughness values. Maximality. This logarithmic entropy, exponential entropy attain maximum value of unity if and only if the roughness values are unity. So if both of them, one of them 0, other is 0. If both of them are unity, then it's a unity. Otherwise, but if both of them are 0, then it is 0. The symmetry, they are symmetric around roughness of X and its complement set. Monotonicity, they are monotonically non-decreasing function. Concavity, both of them are concave functions. So these are the properties. Now let's see entropy measure if you plot it. Logarithmic entropy, exponential entropy. If you look at the roughness of A, roughness that means the complement is set X and it is complement set. So if we take cross section, that means roughness of A equal to P. So you see the roughness equal to P, we get this plot. And roughness equal to A equal to B equal to 1, when all are 1, then you get maximum value 1. When all are 0, we get 0. And it is symmetric around this axis. So plots of entropy for different values of base function, etc. Now, if you look at what does this entropy signify? Basically, it quantifies the incompleteness of knowledge about the universe with respect to the definability of the set X. So the way I have said defined with respect to definition of, given the definition of X, the entropy quantifies the incompleteness of knowledge about U. That is, it measures the gain in incompleteness. Gain in incompleteness. Therefore, in order to have a decision making, I would like to minimize this gain in incompleteness. So obviously, rough fuzzy entropy has significance in data analysis, granular mining for uncertainty, and it is a very catchy word. And once you have data, whether it is a biological data or astrophysical data or image data, uncertainty is inherent. It can come from incompleteness information. vague information, noisy, so many factors. Therefore, if there is a fuzziness in the region object, if it is a granularity, etc., then you can use this. If there is no roughness, then you can go all simply by the fuzzy entropy. If there is no fuzziness, only go by the rough entropy. But again, I'm not considering probabilistic uncertainty. To take that on the top of this, then it will be much more powerful. Now let's come to several applications. Let's consider plus image analysis. Very, very simple example because many of you are working on image always for the last 3 decades, I have seen. So first, see why rough fuzzy entropy for image? You ask yourself. First of all, we see that fuzzy boundaries of region. Therefore, fuzziness comes into picture. We can see that rough dissembles between nearby granules, rough dissembles between nearby pixels. What is this? Any pixel intensity tends to attain its value as close to its neighboring value. This is the property of any image we consider. Any pixel intensity tends to attain its value as close to its neighboring one. That means there is a question of resemblance between nearby gray level. Similarly, any level, gray level, say 7 is close to 8 and 6, 8 is close to 7 and 9. So any intensity or gray value is close to its neighboring values. So there is a question of rough dissemblance. So therefore, I can incorporate this fuzziness is boundary because of the sinusoidal carrier background and rough dissemblance of between nearby variables and rough dissemblance between nearby pixels. And nearby variables, as I mentioned before, have limited discernibility. A region containing gray values separated by 6 gray levels. Here, this is naked eye cannot discriminate, but here you have 6 consecutive gray levels. Another nice example of showing roughness or image, that in an image, when you discretize, when you in image, when you have sinusoidal, that is responsible for fuzziness. Now, when you discretize x-axis and y-axis in terms of 1 to 9 and 1 to m, 1 to n or 1 to n, and also you discretize the label L into 1 to L minus 1, that means you are incorporating granularity. Very, very, very nice example. So when you have sinusoidal information, it is responsible for fuzziness. And when you are discretizing the x-axis, y-axis, and L, so you are making it is granulated one. Therefore, that introduces Offset theory. So that means in an image, every pixel can be considered as a granule. In a final level, in a coarser level, any region can be considered as a granule. So these are concept of granules. And that means why rough fuzzy entropy can be considered as a tool of certain modeling for image analysis. Example applications of granular. I mean, there are so many image and video I will explain in detail. Rough fuzzy clustering, image segmentation, generalized offset for object extraction, video tracking, granular flow graph, adaptive rule generation, unsupervised. Then rough filter, it's a new concept, interstatic entropy. Then in bioinformatics, I will get one active I cover fuzzy information measure for microRNA selection or gene selection, one thing. Then I will use crisp granule, fuzzy information granule. I will show the example of upper and lower approximation. I will show the role of granular size, lower approximation. That means, as I mentioned, granular computing depends on the how do you define the granule, the granular size, shape, etc. And I will also explain the role of lower and upper, because lower means definitely belonging, upper means definitely as well as possibly belonging. So lower and upper takes care of uncertainty handling, and your this information granule takes care of the granular computing aspect. Similarly, social network, if I get time, I will explain the community detection problem, simple one. Lead prediction, I may not get time. Let's see. Now, image and video analysis. Very slowly, we just listen one. So there are many ways. First of all, one is pixel classification based segmentation. One is could be segmentation based segmentation. So, and then tracking could be segmentation based, tracking could be classification based, tracking could be prediction based. So let us go one by one. So first I'll explain rough fuzzy clustering and object extraction. That means I go just object extraction, that is segmentation. And why is segmentation important, as I mentioned to you, it is because it is a clustering. Clustering is an unsupervised. And clustering is no more a subject of computer science or electrical engineer today. When we subject originated in 1960, that time it was a subject of electrical engineers. But today, it is a must subject for anybody who is handling data. Because given any data, without knowing anything, without knowing its size, without knowing the number one, what you do? You first try to make it cluster so that you see if there is a pocket and etc. So clustering is a must component for today. So I will explain why rough fuzzy clustering is important than ordinary clustering is semis, and then fuzzy extraction, pixel classification method. Then I will explain image ambiguity measure, as I explained rough fuzzy ambiguity measures for object extraction and then used for video tracking. It will be for segmentation based method, unsupervised. Then I will say by rule based classification based method for unsupervised tracking. That I do not have any idea about the object tracking. It's challenging. Then I will go by the prediction based method when the four objects are occluded, complete occlusion, complete overlapping. How do you identify them? So these are explained one by one. So first and there I will explain the role of granules, that is window size, how to find the coordinate decomposition, how to find the arbitrary shape, that is the region growing, then the role of lower approximation. Why? Because it indicates the definitive belonging there. So for unsupervised method, it is very useful technique. Without do not know, you try to find the lower approximation based on your intuition first. So before I go further, let me explain the concept of neighborhood granule in a feature space. This is a two-class problem, blue and red. So for every pixel, every point, I can define a granule as marked by the one, two neighborhood granules centered around x1, x2, feature space. Phi is the radius of the granule, and this is a P norm function. Granule's shape and size, it's a distance function. So depending on the what kind of distance, whether it is a city block distance or coordinated distance, that is P norm distance function, and threshold, we determine the granule shape and size. So for every point, I can divide a granule. So it is a neighborhood granule. It's called a neighborhood granule. That means you take a point on it and then see within a distance of phi what are the granules are there. So this is a granule centered around. Similarly, around this point you get an overlapping granule. Around this point you get an overlapping granule. That means you are taking care of the overlapping as much as possible. So this is used for further modeling the overlappingness of just granule. So this will be also I will be explaining in sometimes. Keep in mind if granules. So rough fuzzy clustering. What is rough fuzzy clustering? Now go back to semis clustering, for example. Semis. What is semis clustering? You assume C. Number of clusters is C equal to 2. Then given a data set, you find first 2 points. First 2 points coming to you as my 2 seed points. Then I cluster all other points around this class depending on the minimum distance property. That means I compute for every point distance from this 2 cluster to seed points and then see to which class it is minimum distance. So I train it. So that's how I get 2 cluster. Then I modify the cluster point, centroid. I compute the centroid. Then I again recluster the entire point. That's how I continue till in the next 2 consecutive stages I get a difference between the cluster centers is less than error, less than epsilon, some value. That means it's some threshold you put and then you say it is my cluster. This is called hard semis. That means you have derived 2 crisp cluster. That is, this pattern goes to only one class, one of the two. Similarly, if you have got C equal to 3 clusters, similarly you take first 3 points as the seed point, and then you split the entire data set around these 3 points. Then you modified those centroid value by these new samples. Then you get a new centroid values 3. Then you again classify the partition, the entire feature space around these 3 centroid values. That you continues because it is an adaptive system, and then you see that when the pockets are pockets are well defined, and then you see that there is no change in the centroid value between 2 consecutive class as determined by an epsilon or some delta threshold, you stop it. So this is called my hard Siemens algorithm. This is very useful. Now, fuzzy Siemens came forward. He said, no, a pattern can go to more than one class. Don't push it forcefully. So for n sample C class problem, I get a C by n matrix. Then every pattern has a membership value to these C classes, C number of classes. For every pattern, I get a C dimensional membership value. Then out of this membership value, I have defined some objective function, and then I try to optimize it. Minimize, and then I say, this is my fuzzy partition. I do not call it this partition. I call it fuzzy partition. That means I get this optimal number of centroid, and around that I get this membership values. That's my one. And that has very wide application for remote sensing, medical imaging, because regions are overlapping. So in case of rough fuzzy clustering, what do we do? Then rough clustering people came into picture. Rough. They said, no, we'll have lower approximation, upper approximation. Accordingly, they did it. And somebody did lower, upper, both should be fuzzy. We said, no, our clustering is different. Now let me explain. So what we do, we define class exactness in terms of granules. That means granules are used for defining class exactness. That means lower approximation. Class exactness. And clustering is, as I mentioned, it's a basic module for data analysis and mining. Now, no one can claim that it is our topics. It is for anybody's topic. And fuzzy sets enable handling of overlapping partition. Rough sets deal with vagueness and incompleteness in class definition, and improved performance and faster than fuzzy clustering. Our objective is that what we will do is much faster than fuzzy. So therefore, wherever fuzzy clustering has been used, it has an edge. So this is our machine learning point of view. It's a granular domain. This is my cluster. I define this is my lower approximation because I consider that the objects which are definitely around the centroid point that I defined. I would define, I compute the membership values for all patterns and detect all those membership values which are greater than the average membership values. And those points, I put them in the lower approximation. There are many other ways you can do. So this is my lower approximation. Cluster 1, lower approximation. Obviously, this is my upper approximation. And this. So what is rough fuzzy clustering? I integrate the concept of membership functions of fuzzy set, concept of lower and upper approximation of rough sets into the concept of hard clustering. So I have hard clustering in the market, I buy it, I incorporate on the top of that fuzziness in membership. I incorporate roughness in lower and upper approximation, that I integrate the concept of membership functions, membership values of fuzzy set theory, because I consider the set is fuzzy, the cluster is fuzzy. I integrate the lower and upper approximation of rough set because I consider that the set has a lower and upper region, which is definitely and possibly. So I take those one and I put it in hard clustering concept. And while fuzzy sets enable handling of overlapping condition, rough sets deal with vagueness, incomplete information. So what I do for a lower approximation, I give membership values all 1 for this cluster. No fuzziness, because I deliberately design them as lower approximation 1. Only I put membership value in 0 or 1. So in case of fuzzy clustering, when I put for every element membership value is a 3-dimensional vector, here I said no. For membership value, when you compute for this lower region, here all membership values will have membership value 1. But for upper minus lower, here we have got membership value 0 to 1. So as a result, when you compute the centroid value of all other clusters, what do you consider? You don't consider this sure value of this cluster for computing centroid value for other. You only consider these values for computing centroid of this cluster. But for this boundary region, you use their membership values to compute the centroid value of these clusters, and everywhere, but with a less weight because they are from boundary. So very simple concept. Only objects in boundaries are fuzzified. Assign membership value 1 for objects in lower approximation and 0 to 1 for those boundary region. Assign higher weight for objects in lower approximation as compared to boundary in computing centroid. Obviously, when you compute the centroid of this class, we get maximum membership value for the centroid for the lower approximation, but here since we have a weight, we get less weight for their contribution for this computation here. But when you compute the centroid value of other classes, then this lower approximation has no impact there, only the boundaries plus their own centroid. So, an influence in computing centroid of own and other cluster, how much it will be? For those from lower region, only on own centroid. And for boundary, on all centroids. That means these boundary values, they have more privilege. They can contribute to centroid computation of all classes, though their impact will be less. But for the lower approximation region, they are only safe for the own class centroid, not for any other class. So each cluster in rough fuzzy is characterized by triplet: a cluster prototype, a crisp core, that be lower approximation, and a fuzzy boundary. Very interesting. If you go for fuzzy CMS algorithm, you get a cluster prototype and it's a fuzzy boundary. If there is no crisp core. If you have a hard CMS algorithm, you get only cluster prototype and hard boundary. So one by one, if you look at it, if you have hard CMS clustering, what you are characterized by? You get a centroid point and their boundaries. Even the centroid points tell you just everything. You do not need anything else. If you want, you can say the cluster, hard boundary, because you are one. In case of fuzzy clustering, you get the C1s and the fuzzy boundary, because every pattern has a n-dimensional, C-dimensional membership value. But in case of rough fuzzy clustering, I get a cluster prototype, I get a fuzzy boundary, and I get a crisp lower approximation. Therefore, its characteristics are as follows. Definition. If you take a beta cluster, etc., upper minus lower equivalent, the union of lower approximation of beta cluster, union of upper approximation of all cluster will be the universe, upper. The intersection of lower approximation for ith cluster and kth cluster, it will be a non-empty set. It's an empty set because there is no intersection. Keep in mind, intersection between two lower approximation will be always a null set. Similarly, intersection of lower approximation of one cluster and boundary, that is also null set, because here and here no overlapping. It's crisp, different boundary. And for every I and k, where I belongs to beta cluster and k belongs to another beta cluster, boundary between two, that is boundary of a cluster, ith cluster, intersection boundary of beta cluster will be non-empty, because there will be an intersection always. And for every element xi, xj belongs to the lower Roughness estimation, membership would be always 1. And every element belongs to the boundary, membership will be 0. So these are the characteristics of rough fuzzy clustering. What is basically is boiling down to, it provides a balanced mixture. It provides a balanced mixture between restricted partition of hard clustering and descriptive partition of fuzzy clustering. Fuzzy hard clustering was restricted. That means either you yes or no, hard. In case of fuzzy clustering, it's a descriptive. Every pattern can go to any class. But rough fuzzy clustering, it's a balanced mixture between two. Not hard completely, not completely fuzzy. Therefore, it is faster than fuzzy clustering. Of course, slower than hard clustering. Faster than fuzzy clustering, and therefore better uncertainty handling performance. And therefore, wherever fuzzy clustering has been used for the last 3 decades, 4 decades, you can use it for without any doubt. It will give better performance in terms of time and also accuracy. Let's consider brain MRI image. Brain MRI image is an advanced medical research institute, Calcutta. It has got 4 regions: background, white matter, gray matter, and cerebrospinal fluid. Now, initial value of delta, I will explain what is the delta. Delta is the first 2 membership values. First 2 membership values. So when you compute the membership values for every pattern to belonging to 4 clauses, and you take the first 2 membership values difference. The difference initially will be less, but as iteration goes on, it will be more. That means the separation will be more. I will show in the graph. So if you look at this, SCM, hard C means, fuzzy C means, rough C means, that is where lower and upper is crisp. And this is another guy, is a lower and upper, both fuzzy. And here it is lower is crisp, but fuzzy. DB index, I will explain what is DB index. DB index value should be less, Dunn index should be more, beta index should be more. I have explained already beta. So higher value of beta means beta segmentation or a fixed number of C. Dunn index should be more, DB index should be less. So you see that for the one, DB index is less, Dunn index is more, this index is more. Now, what is DB index? Let me first explain other. DB index, you see that, look at the definition of 1. So you take VI is the variance and this is the distance. So every cluster VI, you compute the variance, and between the 2 clusters, you got the distance. So you take the, so that means you that by variance should be always less and distance should be more. So this ratio should be less. So lower the value of DB means better is the partition. Similarly, non-index is the numerator is distance. So the separability between 2 clusters should be more and the variance should be less, homogeneity. So higher the value of D, it's better. So that's what I mentioned the one. And now if you look at these other images, it's for one image we showed all the 5 images. Similarly for original SCM, 4 more other images. Look at the image culture. There also you can see the one rough fuzzy cement, one FCM rough cement. This shows the pictorial result. It's input. Similarly here also you see that this is the original image. I get the separated. The best output. See, you get this one, brain MRI image. Similarly, look at this beta index. So results for brain MRI image. image. You compute dB index for different values of 1. I take more other images. You look at this hard image, fuzzy image, rough image with crisp lower upper, rough image with fuzzy upper lower, the rough image with crisp lower, fuzzy upper. Look at this one, dB index is lowest, all cases. Turn index, maximum in the proposed method. As usual, if you can see that one, it is competition time wise, so beta index also. So in all cases, all in terms of index values, the proposed method rough fuzzy clustering, which gives a balanced mixture between hard restrictive hard clustering and descriptive fuzzy clustering. Similarly, competition time-wise, if you look at this, interesting, hard image is lowest because it goes only 0 or 1. Fuzzy is maximum because you have to compute every time membership values. And then rough lower is next because it is a crisp lower upper. This is more fuzzy upper lower. This is in between. Same is picture is reflected here. Now look at the highest membership, second highest membership. At first iteration, when you find this one, you see that these two values are very close. That's why if you plot it along x-axis, 45-degree angle, x equal to y, see that values are here. And after iteration, with the value number of pixels was 460, c equal to 4, delta equal to 0.45 at iteration and delta 6.5 at just final iteration. See, after final iteration, you see that highest values are much widely apart from the second highest. Initially, they are very closed, almost equal. Very interesting. Highest membership values. So you see the average difference delta between two highest membership of pixels at 1. Now, should I continue? Can you take it?
Sir, I think we can stop now.
Yeah.
Because we have, and now we'll take some questions, sir. If
okay.
You don't, if it's
sure.
okay with you.
Sure,
okay.
Sure.
Okay, so dear participants, so the second session of the lecture series of AICTE Distinguished Chair Professor scheme is completed now. We'll have another session again on 29th of January. And if you have any questions, can you please post it in the chat? So, yes. Okay, even we have put up the feedback form. So please, fill your feedback forms. And if there are any questions, kindly put it up in chat. Or you can even raise hands and Dr. Shalaka can unmute you to ask any questions. I think they have, nobody has put any questions, sir.
Is it difficult to understand or no? Huh?
So
even if it is a just naive question, you may ask. Even if it is a very naive question, you think that don't hesitate to ask.
yes, I would request some of the members to please ask questions. Okay, till they post questions, I'd again mention about our data analytics in healthcare course, which is a 3-month online part-time course, 2 days in the weekdays in the evenings and weekend on Saturday. So the batch is starting on 2nd Feb 2022. This is our 7th batch of online course, and you will get the details at bcp.edu.in, our website, under courses available. So I think there are no questions, sir. So I take this opportunity to thank Professor Shankar K. Pal for his very enlightening lecture on a topic which is relatively very new to the pharma field. And I would also like to thank each and every delegate who has been present and who have been part of this particular lecture series. Thank you all. And we'll meet again at 3 o'clock on the next Saturday, 29th January 2022, for the third and concluding session of the AICTE Distinguished Chair Professor Lecture Series. Thank you all.
Thank you.
And please fill in the feedback form before you leave. Thank you. Okay. Thank you, sir.
Thank you very much. Thank you. Should I? Can
Sir,
I
you
leave
can
now?
leave. Yes, sir. Yes, sir.
Thank you. Thank you.
There are many who are telling thanks to you, sir, in the chat.